Today's talk's going to be continuing on from the series of talks I've been giving so far about trying to find a polynomial that's equivalent to the Kullback-Leibler divergence, or the loss function for a statistical model. So in the first talk, we introduced polynomial rings and the Hilbert basis theorem, which we then used in the second talk to find conditions which guarantee that the KL divergence for a model is bounded by a polynomial. So I'll just remind everyone of the main points of that. So the title of the talk is continuing on from before. It's from analytic to algebraic, part 2. Okay, so we had, given a statistical model, we had the analytic loss function, the KL divergence, and we'd seen in the second talk that when you can write your model in terms of a certain series, and when parts of that series converge, you get an upper bound of the following form, where the Kullback-Leibler divergence is bounded by an infinite sum of polynomials. And so the problem we've been trying to understand is when can we bound that by the sum over a finite subset of those polynomials. And so the argument we had for finding such a bound was that the Hilbert basis theorem tells us that we have infinitely many polynomials. The ideal they generate will have a finite generating set, and so each of those polynomials can be written in terms of the first, say, capital J of that sequence, where these A terms are also polynomials, which are called the quotients. And so the condition that lets us guarantee this second upper bound, we found that if you can add up the squares of all those quotients, and if you can bound that by some real number for all parameters in the weight space, then you can guarantee that this second upper bound holds. And so you can bound the KL divergence by a polynomial. And so to be able to check this condition, we need some methods of actually finding out what these quotients are, or finding specific values of them so we can plug them into this series and see if it converges and is bounded. And so last week I talked about the polynomial division algorithm, which is sort of the main way we would try to find values of the quotients. So we would take each fj and divide it by that finite subset, f0 to f capital J, to try and find the quotients. But at the end of the last talk, I mentioned that the polynomial division algorithm has some problems. So the polynomial division algorithm has some issues. So specifically, we can't use it straight away to find these quotients exactly. So it may be true that you have a polynomial in the ideal generated by, say, F1 to Fj. And so that just says that you can find there exists an expression of this form, but the division algorithm might output basically a non-zero remainder, so it might output an expression of the, or I'll give you quotients.
Sorry to interrupt, Spencer.
Yeah.
Irritating technical point. The thing above your head is about to obscure the board, the microphone indicator. Maybe if you could walk back over to stand on top of the orb or nearby the orb, then it won't be in view. Thanks.
Let's see. So if I... Oops.
Yep, that's perfect.
That's good. Okay. So the division algorithm might output quotients that give you an expression that looks like this. So it, oops, wrong thing. Where it has a non-zero remainder. And so if this happens, we can't really use these quotients in the series to check convergence for an upper bound. So I'll go over to the next board and just remind you, I think, of an example I think I briefly talked about at the end of last talk. So an example of this happening was the polynomial p equals minus y squared plus z. F1 equals xy plus z, and F2 equals x plus y. So it's true that P is in the ideal generated by F1 and F2. Specifically, P can be written as F1 minus y times F2. However, the division algorithm outputs P equals 0 F1 plus 0 F2 plus P. So P is the whole remainder. And this is if you're using, say, lexicographic or graded lexicographic monomial order. And so, yeah, if something like this happens, it's not very helpful for the calculation we're trying to do. And so to try and prevent this problem, Gröbner bases are often used. So I think they were defined to basically fix this issue. So I will define them here. So there's first a couple of definitions we need before I introduce Gröbner bases. So also from now, I'll assume that we've picked a monomial order and holding it fixed. And so I guess, yeah, for the later parts of the talk, I'll be using graded lexicographic order. So if I is a polynomial ideal, we define the set of leading terms of I to be the set containing the leading term of each polynomial that's in I. And so we can also think about the ideal that the set of leading terms generates. So what can happen so by the Hilbert basis theorem, each polynomial ideal can be finitely generated. So if I is, say, generated by these polynomials, it may be that the ideal of leading terms of I does not equal the ideal generated by the leading terms of the generators for I, F0 up to Fj. So this is actually what happens in the example at the top of this board. So the leading term of P is minus y squared, while the leading terms of F1 and F2 are xy and x. Neither of these two monomials divide minus y squared, and so the leading term of P doesn't lie in the ideal generated by xy and x. And so this is really the cause of the issues that can happen with the division algorithm. So a Gröbner basis for the ideal I is a generating set for I. So that means that the ideal generated by those polynomials equals I, but one which has the property that the leading terms of that generating set generate the leading term ideal for I. So I'm just going to move over to the next board. And so a couple of properties of Gröbner bases. Firstly is that they always exist. So if you have a finite generating set for a polynomial ideal, there's an algorithm called Buchberger's algorithm, which lets you add new elements to that generating set and turn it into a Gröbner basis. And the other property, which is the important one for us, is that if f is in the ideal generated by a Gröbner basis, so if we have a Gröbner basis for an ideal, and we take an element in that ideal, dividing f by that basis always outputs a zero remainder, so it always outputs quotients which satisfy f equals q0, g0 up to qs, gs with no remainder. And so that's exactly what we need to be able to find the quotients and then check the convergence of the series in the problem we're studying. But just a slight technical point first, the polynomials that we're looking at in our problem, so these are the fj of w's. They come from, if you remember in the second talk, they come from writing the regression function for a model minus the true functions as a series of polynomials times linearly independent functions of the input. So coming from that series, there's no guarantee that if you take the finite subset of those polynomials which generate the whole ideal, there's no guarantee that that is a Gröbner basis. But the following lemma tells us that we can take that generating set and replace it by a Gröbner basis without having any effect on the RLCT on the RLCT, which is the final thing that we're trying to calculate. So the lemma says that if you have two finite generating sets for the same polynomial ideal, then there exists two constants so that C1 times the sum over the fj squared is less than or equal to the sum over the gj's squared, and that's bounded by C2 times the sum over the first generating set squared. In other words, that's saying that the two sums, or these two polynomials, are equivalent according to the Lipschitz equivalence definition from previously. And so that means that if we can instead do the calculation using the quotients to check the upper bound, we can, we can instead check the upper bound for using this Gröbner basis, and that will be equivalent to the upper bound using the basis of the polynomials coming from this, writing this series up here. Okay, so I'll just go over to the final board. So at the moment, it looks like, given a model that we can write in a series of that form, the process we could do to try and find a bounding polynomial for the Cal divergence is first find a finite generating set, which I should mention is actually can be quite difficult to actually do. It's only the Hilbert basis theorem only guarantees that one exists, but it's actually difficult to work out what actually works in actual examples. Then we can swap that with a Gröbner basis. Then we can divide each, so we have a sequence of infinitely many polynomials. We can divide each one by, I'm just going to write that Gröbner basis as the set capital G. We can divide that each polynomial in our sequence by the Gröbner basis G to get expressions of the form HA0, G0, and so on. And lastly, we can check, once we've found all those quotients, we can check when we add up all their squares, we can check whether that is bounded by some positive real number. So at this point, we weren't really sure whether to go ahead and try this with examples of models, or whether we needed to first do some more work. So the main sort of issue that caused us to stumble is that the quotients are not unique. So there could be lots of different sets of quotient polynomials that they'll let you write expressions like this. And so I guess an example of how that can happen is specifically the division algorithm depends strongly on the chosen order of the divisors. So if you remember how the division algorithm is sort of set up, you start by writing the divisors in order on the left. And the first thing you do is you look at the leading term of the polynomial you're dividing and check first whether the leading term of the first divisor divides it. If it does, you use that to cancel it out. If it doesn't, you go on to the next divisor and see whether its leading term can be used to cancel the leading term of p. And so if you were to reorder these divisors, you'd usually get a different set of quotients out from the algorithm. And so since we're trying to check the convergence of this series, it was quite unclear whether, say, if we did compute it for an example, it would be unclear whether if its conversion was bounded, we wouldn't know if that was just a fluke because of the order of the divisors we happen to use. And similarly, if it didn't converge, we also wouldn't really know whether that just happened to also be a fluke. So instead, we first investigated ways of making the division algorithm work independently of any chosen order. And so I'll introduce what's called the generic division algorithm for that. I should say at the moment it's unclear whether these the following methods are necessary or crucial for doing calculations. We don't really yet know how much of an impact this non-uniqueness can have on the convergence. I guess, yeah, I should say I haven't found any examples where choosing different quotients does change the convergence, but I also haven't been able to prove that it doesn't matter either. So I guess, yeah, quite a bit of it's unclear, but I guess regardless of that, I think the maths underpinning the generic division algorithm is still quite interesting, and it is interesting to see it work in examples. So I'm going to go back to the first slide to introduce that. Okay, so the generic division algorithm, it's a modification of the standard polynomial division algorithm. So this was, I think, developed by Dan several years ago for another project. And while we were studying this problem, Dan realized that, oh, maybe this could be quite useful here. So for the rest of the talk, I'm going to use graded lexicographic monomial order. You can use any monomial order that has the property that if you pick any monomial, there's only finitely many smaller monomials. And so that's the case in any graded order. because there's only finitely many monomials of each degree. So in the standard division algorithm, if we have the what's called the intermediate remainder p, so that's just whatever is left over on the right-hand side of the calculation while you're doing long division. So that's what's left that's the sort of polynomial that's left there at each step. What we do at each step in the standard division algorithm is we subtract the leading term of p divided by the leading term of fj times fj, where fj is the first divisor, whose leading term divides the leading term of p. So in the generic division algorithm, instead of just choosing one divisor and subtracting this expression from the intermediate remainder p, we instead average over all the divisors that work. So in the generic division algorithm, we subtract. So I'll explain what this notation is in a second. So capital D alpha is the set of all integers. So this index runs over the divisors, and the set D alpha just records which, I just realized the way I've written it doesn't make sense. Sorry, I'll just fix that up. Okay, so instead of writing the leading term of P up here, I'll write P alpha x to the alpha. So P alpha is the coefficient of the monomial x to the alpha in the polynomial P. And so then capital D alpha is the set that records which of the divisor's leading terms divides the monomial x to the alpha. And little d alpha is just the number of elements in that set. So when we subtract this polynomial from P, we're essentially doing the same thing as in the standard division algorithm, but instead of picking a single divisor to use, we're averaging over all the divisors which have leading terms which divide that of P. And so I'll go to the next board and write the whole algorithm out. So the inputs to the algorithm are the divisors, and also a polynomial f, which is the polynomial that we're dividing by the divisors. And so the algorithm outputs quotients. So I write them as A0 up to AS. And it also outputs a remainder R. Okay, so the first thing that the algorithm uses is it defines a set called capital lambda, which first starts with the largest monomial in F. So F is a linear combination of different monomials, and so we just take the largest monomial in F and record its index, which we'll write as alpha 1. And then this set contains every monomial which is smaller than alpha 1. And since there's finitely many, and the smallest one will be 0, we can just write that set as alpha 1 up to alpha q. And so the algorithm begins by setting the quotients all to 0. And the remainder is 0. And setting this intermediate remainder p as all of f, which is the polynomial we're dividing. And there's just an index which keeps track of what step we're at. And so at each step, we will increase that index and we'll subtract from P that average that I described in the previous board. So also for a step to occur, we also need that there exists some divisor whose leading term divides x to the alpha. If there are no divisors that divide x to the alpha I, we just move on to the next index in the set, capital lambda. So we replace the intermediate remainder by subtracting the average of all those polynomials using each of the divisors whose leading terms divide x to the alpha I. And then we also update each quotient based on that subtraction. So for each divisor that is used in that previous step, we update the quotient for it. And so then this like for loop and while loop, we increase the value of the index I, and then the while loop ends. And then for our space, I'll go to the next board. The algorithm outputs the final value of P as the remainder, and it outputs the final values of the quotients. Okay, so the following proposition says that this generic division algorithm works just as well as the standard division algorithm. So firstly, the remainder and quotients that it outputs satisfy the equation that the original polynomial equals the quotients times the divisors plus the remainder. And the remainder satisfies the same conditions that it does for the standard division algorithm. So R consists of monomials, none of which are divisible by any of the leading terms of the divisors. And additionally, if one of the quotients times the divisors is non-zero, then the leading term of the original polynomial we're dividing is always greater than or equal to the leading term of that quotient times divisor. And since at each step of the algorithm we use the average over each divisor, the output of the algorithm is then completely independent of any chosen order of the divisors. And so one thing that this algorithm lets us do is sort of work backwards and find general expressions for the quotients. And so then we can use these expressions in actual examples of statistical models to try and check the upper bound conditions. So first, a bit of notation, which we'll be using. So if the leading term of fj divides x to the alpha, we write tau alpha beta j as, so we have this polynomial x to the alpha divided by the leading term of fj times all of the divisor fj. We can take that polynomial and check the coefficient of x to the beta in that polynomial. And so we write that as tau alpha beta j. So that's a real number. And then we define tau alpha beta with no j as the sum over all of the divisors whose leading term divides x to the alpha. We add up all those tau alpha beta j factors. And if the set d alpha is empty, so in other words, no divisors leading terms divide x to the alpha, then we set tau alpha beta as 0. So I'll go over to the final board. So let's write pi for the value of p at the ith after I steps in the algorithm. And so from how the algorithm works, so we start with p0 equals f, and then just by looking at what the algorithm does in the first step, we have that p1 is equal to f minus 1 on d alpha 1. So we minus the average over all of the divisors whose leading term divides x to the alpha 1, and then we have this polynomial f alpha 1 x to the alpha 1 divided by the leading term of each divisor times the whole divisor. So I'll refer to this 1 and d alpha 1 as a averaging factor. Okay, so then using this we can try and calculate P2 and P3 and so on, and doing so will let us figure out an expression for Pi in general. So the first thing we need is the coefficient of x to the alpha 2 in P1. And so using the above expression, this will be the coefficient of x to the alpha 2 in f minus f alpha 1 on the averaging factor times the sum of over the divisors, and then we have the x to the alpha 1 on the leading term of fj times fj, and we take the coefficient in that polynomial of x to the alpha 2. But the term there, the coefficient of x to the alpha 2 in the polynomial within the parentheses is exactly the tau alpha 1 alpha 2 j term that we defined on the previous board. So this can be written as f alpha 2 minus f alpha 1 on d alpha 1 times the sum over the divisors in d alpha 1 time we sum over tau alpha 1 alpha 2 j, and then if you remember, this whole sum just equals tau alpha 1 alpha 2 without the j subscript. Okay, and so the reason for calculating this expression for the coefficient of alpha 1 in, the coefficient of alpha 2 in P1 is that we can use it to compute an expression for P2, so the value of P at the next step in the algorithm. So P2 equals P1 minus the sum over divisors whose leading terms divide x to the alpha 2. We have the averaging factor for that sum, which is d alpha 2. The coefficient of P1, the coefficient of alpha 2 in P1 times x to the alpha 2 on the leading term of the divisors times the whole divisor. So we can take this expression we found for the coefficient of alpha 2 in P1 and plug it in here. And so if we go back to the first board, after a few steps of rearranging, what that comes out as is P2 equals F minus the sum over, we have a new index T, which just sums from 1 to 2, and then we sum over those averages. And we have these familiar looking polynomials in each summand. And then there's also a sum over the divisors whose leading terms divide x to the alpha 2. The coefficient of alpha 1 in f. And then we have a pair of those averaging factors. And then this tau alpha 1, alpha 2. And so this is coming from just before the, in the coefficient of alpha 2 in P1, we saw that there was this tau alpha 1, alpha 2 factor. And then this is all multiplied by the polynomial x to the alpha 2 divided by the leading term of fj times all of the divisor fj. So we can keep going. So we can see what the coefficient of x to the alpha 3 in P2 is, and then plug that into the expression for P3. I'll skip the working, but what it comes out as is P3 is the, it equals f minus, we have a sum of index t equals 1 to 3. And then this term is very similar to this term in the expression for P2. So we add up over all the divisors whose leading terms divide alpha 1 or alpha 2 or alpha 3, and then we have the same polynomials as in the P2 case. Then there's another term, which is then the sum over all pairs of integers, or all distinct pairs of integers in ascending order between 1 and 3. And the sum is then very similar to this second term in P2. So we sum over the divisors whose leading terms divide the alpha t, where alpha t is, comes from the larger integer there. And we then have a pair of averaging factors associated to each of those integers. We take the coefficient of f related to the smaller integer, and then we have the tau term coming from the pair of indices. And then, so P1, we subtracted 1 sum from f. P2, we added and subtracted 2 different sums. And so for P3, we then actually have a third sum, which is the sum over all divisors whose leading terms divide x to the alpha 3. And this sum, each term has a triple of averaging factors associated to each of the indices alpha 1, alpha 2, and alpha 3. We take the coefficient of f associated with the first of those indices, and then we have two pairs of these tau terms associated to each adjacent pair of indices, and then the usual polynomial at the end. Okay, so from these first three values of P1, P2, and P3, a pattern seems to be forming. So in P3, the first sum involves all single indices between alpha 1 and alpha 3. The second sum involves all distinct pairs of indices, so like alpha s and alpha t. And the third sum involves all triples of distinct indices when placed in descending order. So we can try and gather from those three examples a general pattern. And so we propose that the expression for p after I steps is f, and we subtract from it the sum of over all single indices between 1 and I. And then we have this usual sum over polynomials that we've seen quite a lot now. And then we add up over what we can call all chains of multi-indices of lengths m equals 2 up to length I. So I guess what I should say is a chain of indices is a collection of multi-indices in descending order according to graded lexicographic order, and where the first indice beta 1 is smaller than alpha 1, which is the leading term of f, and the final indice is larger, greater than or equal to alpha I. And then we sum over each divisor whose leading term divides the smallest indice in the chain. And then there's as we saw in P1, P2, and P3, there's a alternating sign based on the length of the chain. We include the averaging factor for each indice in the chain, and then the tau term for each pair of adjacent indices in the chain. And then we also have the coefficient of the first indice in the chain, and then the polynomial involving the final indice in the chain, or final multi-index, I should say. So this proposition can be proved just by induction, and so it's a similar process of like what we did for finding P1, P2, and P3. And so I'll just go to the next board to finish off the talk. And so I'll sort of discuss the whole point of finding these this general expression for pi. So if I is a polynomial ideal, and G0 up to GS is a Gröbner basis for I, then dividing, say, an element of I by this Gröbner basis using the generic division algorithm. So that outputs quotients which satisfy an expression A0, G0 up to AS, GS, where now we specifically have expressions for each of those quotients, AJ. So AJ is the sum over all multi-indices, such that the leading term of GJ, actually I'll write that as such that J is in D alpha. So in other words, the leading term of GJ divides X to the alpha. 1 on D alpha, so the averaging term, the coefficient of X to the alpha in F, X to the alpha divided by the leading term of GJ. And then we have a sum over all chains of length 2 to infinity. I'll discuss these sums which look infinite in a second. So we add over all chains of multi-indices of length m, where the leading term of GJ divides x to the beta m. So beta m is the final multi-index. We have a alternating sign. Each of the averaging factors associated to each index. The coefficient of x to the beta 1 in F, then all the tau terms coming from that chain, followed by x to the beta m on the leading term of fj. So how do we get this expression? So if we go back to the previous board, where we have the expression for pi, if the polynomial we're dividing, which is called f, is in the Gröbner basis, in the ideal generated by the Gröbner basis G0 to GS, that means that the final remainder, PQ, is 0. So we can just move all of this rest of the expression to the other side, and we get f equals this whole thing circled in red. And then we just collect all the things that are multiplied by fj or gj to find the quotients. And so when you do that, you get these sums written on the final board. And so I guess, initially these two sums look infinite. But so the first sum, f alpha, is only non-zero for finitely many alpha, so this sum is actually finite. And the second sum is actually finite because since we're using graded lexicographic order, there's only finitely many chains of, and they're all of finite length, which also, I guess, uses the property that this f beta 1 term is only non-zero for finitely many indices. So then what we can eventually go and do is use these expressions to calculate the quotients and plug them into that series where we square them all and see if it converges and is bounded. Which I guess, we'll do at some later date. All right, I might finish there. Thank you for listening. And if anyone has any questions, feel free to ask.
Yeah, thanks a lot, Spencer.